Hi, let me introduce to you our game, the game of 15. The rules are listed below. A list of 9 digits will be shown to both players. Each player takes a number from the list. The player must avoid the sum of any 3 digits equal to 15. If both players successfully avoid the sum, the player that gets the last card wins.
Today, we'll be introducing a mathematical game known as the game of 15. The numbers 1 to 9 are first written on separate pieces of paper and then placed on a table. The aim of the game is to avoid getting the sum of 15 using 3 of any of the selected numbers. Let us take a look at an optimal play between two players using 9 numbers. In this example game, player 1 starts off by selecting a number on the table. This action is then followed by player 2, who does the same. As you can see, both players take alternate turns to select their numbers. While selecting their numbers, both players have to find a balance of attack and defense at the same time. This continues until the last number has been chosen. After the last card has been chosen, if no combinations are formed, the player that started first wins the game.
After watching the video, do you have any doubts with what the video is showing like? Why do we choose 15 instead of other digits? What is the theory behind the game? What will happen if we change the list of digits? And who will have a bigger chance of winning? The theory behind the game. First, we group the digits into 3 times 3 grid and arrange in a way that the sum of every row, column, and diagonal equal the grid. In this way, the sum of rows will be equal to the sum of digits divided by number of rows. The formula shown before the division is derived from the sum of arithmetic progression. The n is number of digits. A is the first term. D is the difference between each term. After you get the sum, you divide it with number of rows or columns, and you will get the sum of each row equal to 15. How to win the game? As our game rules states, that winner must avoid getting the sum of any 3 digits equal 15. The first player just need to avoid getting 3 digits in row, column, or diagonal to win the game. Does this remind you of a game that has the absolutely opposite winning credential? Now, we come to the next question. What will happen if we change the list of numbers? The game will still obey the theory if and only if the difference d between every term is the same. For example, if we change the digits to 3, 6, 9, 12, 15, 18, 21, as long as the difference between the numbers like 6 minus 3 equal to 3, 9 minus 6 equal to 3, it still follows the theory. However, if we change the list to random numbers with different differences, the sum of each row and column will not be the same. Therefore, the theory does not hold.
Now let us take a look at the same game using tic-tac-toe as the base. The 9 numbers are placed in the form of a 3x3 grid to show how the game relates to tic-tac-toe. As you can see, whenever a number is chosen, there will be a symbol below. Try to take note of each individual number and the symbol it relates to see if you can spot a pattern. Similarly, the game proceeds accordingly until the last number is chosen. Now, let us take a look at the grid again. Can you spot the pattern? If you looked closely, you will realize that every possible straight line that crosses 3 numbers sums up to 15. Therefore, the winning theory behind the game is to avoid making any of these lines while getting your opponent to make them. This can also be said to be the reverse of a tic-tac-toe game.
So what happens when we increase the numbers to 16 and the combination to 4? Let us assume that we can use the same method as 9 numbers. That way we will need to form a 4x4 square with the same sum of each side. But how do we know what sum do we need? Here is how do we find the sum. First, let n be a positive number that is greater or equal to 3. Let n be the number of combinations. Therefore, we will have n times n numbers. Therefore, we will have the sum of 1 to n square numbers. The total number will get us a formula of n square times n square plus 1 over 2. That way, if we divide by the number of sides, which is n, we will get the sum of each side. So for example, if we have n equals to 4, the sum of one side will be 4 square times 4 square plus 1 over 2 times 4 square. That's where we get 34. So let's get back to the square and see how it works. So in this case, we are able to form a square which has the same formula as the 3x3 square. Do take note that in this example, this is a perfect square where all the 5 subsquares that are highlighted also sum up to 34. So does this mean that the solution works? Well, actually, no. Based on this tic-tac-toe that we formed, there are actually 10 combinations which can form a line to win in a tic-tac-toe, but in fact, there are actually 86 combinations to form the sum of 34 using the numbers 1 to 16. But how is this possible? Well, this is one of the examples that you can see. Just by swapping 4 numbers, we can get the square that has the sum of 34 on each side. So what does this actually mean? Well, in fact, there are actually 880 basic ways to form a 4x4 square that has the sum of 34 on every side. Therefore, we can conclude that this solution can no longer be used for 4x4 square. However, we can still improve our chances of winning by knowing how many times each number appears in the combination, just like for the 9 numbers.
Autonomous computing. Time needed for autonomous computing increase exponentially, as we can see from the following graph. For n times n, there are n square Cn where to form the sum of one side of the square, n square times n square plus 1 and divided by 2n. This is the table of n and number of combinations. From this table, we can draw the graph. As n increase, the number of combinations increase exponentially. Real-world context. Figure 1 above shows a 3 times 3 geometric square. The 3 pieces occupying each row, column, and diagonal have a rectangular target, as seen at left and right, and above and below. Here, the 9 pieces are all determiners, but pieces of any shape may appear, and it is not a requirement that they be of same size. In figure 2, for instance, the pieces are polynomials of consecutive size from 1 up to 9 units. The target is a 4x4 square with an inner square hole.